All right, so what is an isomer? Well, the note is basically, let me summarize this for you. You know, a lot of the organic compounds we did today, last week, sorry, composed of carbon and of course, hydrogen. There's a lot of carbon and hydrogen. We saw that over and over last week. But here's the thing. You can take these same carbons and hydrogens and rearrange them. Now, provided that, let's say something had 5 carbons and 12 hydrogens to begin with. So it had 12 carbons and, sorry, 12, let us call it 12 carbons and let's just call it 24 hydrogens. Let's just assume that, right? What we can do, right, is rearrange the carbons and hydrogens, but even though we rearrange it, at the end of the day, it still has the same amount of carbons and hydrogens. The arrangement alone is different. That different arrangement is called an isomer. But let me show you an example. On the screen in front of you, I would like you all to draw this and send the name of this alkene for me. And I know it's an alkene because it only has C's and H's, well, carbons and hydrogens, and there are no double bonds. Look at the diagram carefully. There are only single bonds. So I know this is an alkene for sure. And I'm seeing the names coming up. What's the name of this alkene? Is it pentane? Is it octane? Is it butane? Right, and a lot of people are getting it correct. The name of this alkene, since there are 1, 2, 3, 4, 5, 6 carbons, his name is hexane. And of course, hex means it represents the number 6. Easy stuff. Here's what we can do now. Let's pretend these things are Lego blocks, and we could take it apart and we're going to rearrange it into a different pattern. So instead of the main chain having 1, 2, 3, 4, 5, 6, let's make it such that the main chain only has how much? 5. 1, 2, 3, 4, and 5. But isn't there a 6 carbon? Not a problem. What we are going to do is take that carbon and link it downwards. So the yellow carbon is not part of the main chain. From last week, right, for me to complete this diagram, how much bonds need to be connected to each carbon? How much bridges does each carbon need to have in any organic compound? And you all are getting it correct. Again, it's supposed to be 4 because I know last week I said it over and over and over. So let's do that. Let me complete the diagram. Each carbon is supposed to have 4 leaving. 1, 2, 3, 4. This one also has 4. Look at it carefully. 1, 2, 3, and the yellow one makes it what? 4. So, and next to each one, well, the yellow carbon also needs to have 4. 1, 2, 3, and 4. And as you all know, at the end of each bridge, it's supposed to have a hydrogen. Let me come. It takes a little while to draw these diagrams. I guess it could be a little annoying to watch me do it. All right. Quick question. The first diagram, I want you to tell me how much carbons it had and how much hydrogens it had. Well, we know the carbon is 6 for sure. 1, 2, 3, 4. But how much hydrogens does it have? Someone said 12 by mistake. It's not 12. All I'm asking you to do is count it up. It has 14 hydrogens. I just take your time and, add up all the H's. All right. Look at the new diagram. Tell me how much carbons it has and how much hydrogens it has. Right? And we followed all the rules perfectly. Yeah? Even though we rearranged the carbons, we ensured that each carbon had 4 bridges or bonds connected to it. We didn't break any rules. The amount of carbon is still 6. 1, 2, 3, 4, 5, and the yellow one is 6. But, no, not but, and also if you add up all the hydrogens, I'm still getting what? 14. So because both of them have the same amount of carbons and the same amount of hydrogens, they are called isomers of each other. That is all an isomer is. You know? I know some of you were expecting something really, really complex, but it's not. You're just rearranging the carbon and hydrogens. Quick question. These, like I just said, these two have a different what? A different rearrangement of carbons and hydrogens. Do you think both of them will behave exactly the same? Like if we were to perform experiments on them and we were to add a certain chemical to this one and then add a certain chemical to this one, do you think both of them will react exactly the same? The answer is no, right? The reason is they may have the same amount of carbon and hydrogens, but they are slightly different from each other. It's like a pair of twins. Twins, let's assume it's not perfectly identical twins, right? And even so, right, if you have a pair of twins, then they are never, ever exactly the same. But even though they look kind of the same, the twins will behave differently, right? They must have different traits. They might have different interests and whatnot. So that's important to know, right? Isomers, even though they're kind of similar, they have the same amount of carbons and hydrogens, you cannot expect them to react exactly the same. Don't get me wrong, their reactions might be similar in some cases, but don't expect exact. Now, here's another thing. Who can tell me what's the molecular formula for the first alkene? The molecular formula is when you put the C and the H, right? And you have the numbers here. Won't it be C6H14? And of course, this one is still what? C6H14. So that's the molecular formula, just in case the examiner asks. You all notice for the isomers, the molecular formulas are the same. That is what this note is saying. But here's the bad thing about the molecular formula, right? Let's say I scroll upwards and somebody now comes to class. So somebody now bounces late into class, right? And I tell them to go in the chemistry store or the chemical store and buy some C6H14. That's all I tell them. Do you think that's enough information? What do you all think? The answer is no, because if I ask them to buy this, when we scroll down, I could be talking about this version, or I could be talking about the version with the yellow. You are not good, that person is not going to be able to tell which one to buy. So for us to clarify that, we would have to give him more information, right? So here's what now. Last week, you learned to name this one. He's hexane. But I also showed you all how to name this one. Notice this one has a branch. Do you all want to take a try at it? What's the name of the new one? Oh, some of you all are getting the answers fast. I swear while I was talking, some of you were typing up the answer. That's good. That's real. Nothing too bad. Remember, whenever there's a branch, the yellow part is the branch. What you need to do first off is concentrate on the main chain, the main part. Now, the main part has how much carbons? 1, 2, 3, 4, 5. And I think some of you all are forgetting that. So yes, the end of the name will be pentane. Now, the branch himself only has 1 carbon. So the branch will be named meth. But all branches end in YL. And where does the branch occur? Some of you all put 1 by mistake. Remember, to reach this branch, the shortest path is from the left-hand side. Which carbon is the branch connected to? Not the first one, but the second one. So it's supposed to be 2. Some of you all put 1 by mistake. How much of you all, well, for those who got it correct, congrats, first of all. But for those who got it wrong, you at least saw your mistake, right? At least let me know in the chat, right? I'm always interested in knowing if you can see your error, because I know once you see your error, you're going to learn it from that point. Great. All right. Now, here's the thing. This diagram has another isomer. Instead of putting the branch here, listen to the question, right? If I were to move the branch and connect it to this one here, what would be the name if I were to move it to this branch here? Right? Because you notice I connected to this one here, right? But if I move it across and connect it to him, it would still have the same amount of H's and carbons and things. Everyone agrees that if I move it to this point where the dot is, I would have to change the 2 into a 3 because it would have been connected to which one? The third carbon. 1, 2, 1, 3. Next question, just to make sure you understand the trend. If I move the chain, the branch, and move it to this carbon, what would I have to change the 3 to? So I move it 1, 2, 3, and that's a trick question, guys. Some of you all are saying it's supposed to be 4 because it's 1, 2, 3, and 4, but that's wrong. And I'm glad some of you all picked up on it one time. Remember, if I move the branch over here, right? If I start walking from this way, it will be 1, 2, 3, 4. But in organic chemistry, when you're naming compounds, you have to take the shortest path to reach the branch, which means you have to start walking from this side. And if we start to walk from on this side, here's 1, the first carbon, and over here is the second carbon. It will go back to being 2. Some of you all forgot that. And some people are still saying 1. It can never be 1 because here's the first carbon, but the branch, the newly placed branch, is at the second carbon from the right-hand side. For those who said 4 and 1 by mistake, please clarify with me if you understand it now, because that trick was from last week, right? So I'm going to give everyone a few seconds, right? And take a 20 seconds and take down anything you need to take down. Okay, so alkenes, which is all we did so far, right? Alkenes, they react a certain way. And on the CXC syllabus, all alkenes burn in air and oxygen. Now, if something burns, and that automatically means when it burns, it will produce a certain amount of heat, okay? Do you know where you can find alkenes in your house? Anybody has want to take a guess? where can we find alkenes in your house? And some of you all got it right off. You can actually find alkenes by your stove. You see those gas tanks? They are filled with alkenes. Now, the type of alkenes, whether it's methane, ethane, propane, I believe the one that you find in your house, those red gas tanks, I believe it's called propane, right? That's the type that they sell off the trucks and whatnot, right? To my knowledge, right? So alkanes can burn in air and oxygen. Of course, we should be really, really happy that alkanes burn, because when they burn, they produce heat, and that heat can cook our food for us. Alkanes also undergo something called substitution reactions. Don't let that big word get to you. I would explain exactly what is a substitution reactions. And alkanes can also be cracked. Its name, the word cracked, means exactly what it is. Enter, if you have something, a big object, and you crack it, doesn't that mean you are trying to break it into smaller pieces? But I will explain it with an example. So for the CXC exam, if the examiner asks you to list the 3 ways alkanes can react, these are the 3 you need to list for him. Alkanes usually undergo these types of reactions. So take down all 3. And of course, I'm going to explain all 3 in detail for you now. Okay? Let me know when you are finished. Yeah. So moving down now. Now remember, we just said that alkanes burn in air. Okay? So let's just, I want to clear up a smaller barrier. How much of you all here can balance equations? Like, you're pretty good at balancing equations. Right. So some of you all are saying yes. Well, you know, I know, expect some of you all are going to say no, right? Today, we will not be reviewing how to balance equations. Now, if you cannot balance equations, not a problem. You just focus for the time being on the actual compounds. Like if it's carbon dioxide I'm talking about, or if it's oxygen I am talking about, don't worry if you can balance it or not. If you are having problems balancing equations, I have a very simple solution for that. All you need to do is go to the school website, go into the chemistry classroom. You'll see me doing it here on the screen. And right below the beginners videos is balancing equations. You have 2 videos. That was going to be part of your homework today in any case. These 2 videos, I did not make it. But the person who did these 2 videos, I could not do a better job than that guy. It was excellent. So even if you know nothing about balancing equations, after viewing those 2, you're going to be set, believe me. So the first thing I had mentioned is that alkenes can burn in air or oxygen. Whenever you burn an alkene, the flame is always clean, blue, and non-smoky. And I could prove that. Well, I don't want you to go and try it now. But whenever your parents are cooking on the stove, go look at the flame. Most of the times, right, provided that the stove is clean, if the stove has a little dirt and whatnot in it, you will see a little bit of yellow in it, right? But if the stove is completely clean, you will notice that the flames are blue. How much of you all have noticed that already? That the flames on the stove is mostly blue. And you will notice that the flame itself, I'm not talking about like if you just light the stove and you stand back, right? And you're not cooking anything on the stove, you will see no smoke. In other words, the flames are clean. And of course, you don't want smoke in your kitchen. The less amount of smoke will be better for you. So that is why alkenes are perfect for your kitchen, right? It doesn't produce any smoke, so you call it a clean flame. So here's it. Anybody wants to tell me what's the name of this particular alkene? CH4. What's the name of that alkene in today's example? That's methane. So whenever you take methane and add it to oxygen, the O stands for oxygen. Remember, for those of you who cannot balance equations, forget about how I got the big 2 in front. All you have to know is the O stands for what? Oxygen. When you take methane and add it to oxygen and you set it afire, you get 3 things. You get CO2, which is carbon dioxide. You get water vapor. You notice it have a little G here, which stands for gas. And this symbol here means heat, which is very important. You don't want to light a flame and the flame has no heat. That's actually almost impossible to imagine, right? Because every flame that you can think about has heat. And you see this heat that you get, that's the heat you use to cook, right? So everyone take down everything on the screen here, right? Even if I take a different alkane, say I take ethane or propane, once I mix it with oxygen, I am going to get these 3 things: carbon dioxide, water vapor, and heat. You'll just get a different amount of carbon dioxide and a different amount of water. But we don't care about the amounts right now. It's just a general reaction, a general format. All right, so let me know when you are finished. Right, so that's the first general format you have to learn off for the exam. The other one, and this is going to take a while, and of course, just by looking at it, it looks scary, right? I will take my time with this one. Alkenes undergo something called substitution reactions. Let's take a few seconds and analyze, what does substitution mean? Let's pretend there's a game of football. Let me say Brazil is playing the world's best team, Germany, right? So let's say that somebody wants to make a substitution, right? What does substitution mean? If you are substituting a player, that means somebody has to come off and somebody has to come on to replace the person who came off. I think everyone should be able to understand that concept. So substitution means something is coming out and something is coming in to take its place. Somebody use a better word, right? In other words, there's a replacement situation going on. Now look at this scenario. Here we have, if you look carefully, this is methane. What the simplest alkene out there. What we are going to do, we are going to mix it with Cl2, that's chlorine, right? Chlorine can be found in the periodic table. Now look at this carefully. I just want to analyze the amount we have of each. This 4 means it only applies to the H. So it has 4 hydrogens and 1 carbon. You notice there's no small number by the C. Whenever there's no small number, it is automatically 1. But no sane person is going to put in the 1 in chemistry. And how much chlorines do we have? We can clearly see it. It has 2 chlorine atoms here. So we go to mix the 2 together. Now I want you to pretend, imagine this scenario up here. I'll break it down simpler. It has 1 carbon and how much hydrogens? 1, 2, 3, and 4. And we are going to mix it with how much chlorines? 2 Cl and a next Cl, 2 chlorines. In the substitution, what's going to happen? One of the H's is going to come out, and one of the chlorines is going to take its place. So it's going to end up looking like this. You have C, 1, 2, 3, but the fourth hydrogen got replaced by one chlorine, and this hydrogen took his place. So you get HCl. Do you all see that? Do you all see the switch over? It's a substitution. Within the methane, the last hydrogen, or at least one of the hydrogens, got substituted out and got replaced by one chlorine. All right. Right. Remember, when I'm explaining this, I know I'm writing out all the H's, but it's just to give you a visual. Are we okay so far? Does everyone see that one hydrogen is getting kicked out and one chlorine is taking its place? Look at this. It has one carbon. How much hydrogens? 1, 2, 3, and one chlorine. Do you all see that over here? One carbon, 1, 2, 3 hydrogens, and one chlorine. And of course, this hydrogen that got kicked out joined this chlorine here to get HCl. That's this guy here. So that's an example of something called a substitution reaction, right? So always look out for that in a substitution reaction. Look for somebody to get kicked out, and of course, whatever gets kicked out has to get replaced by something. All right? So I want everyone to only take down the first line, right? So if you want a kind of definition of what substitution is when something gets replaced. There's a replacement going on. Now, I know some of you are trying to grasp the concept, but I have plenty more examples. So just for the time being, just take down the first line for me, right? And I'm going to slowly do another one for you all. So here's what we have now. You see this compound that we just created that has, it started off with 4 H's, 4 hydrogens, but now it only has 3 hydrogens because one of the chlorines from him took his place. His name at the beginning was methane. Do you think it's fair to call this guy methane also? Do you think his name should still be methane? I don't think it's fair to call him methane because methane has 1 carbon and 4 hydrogens. He only has 3 hydrogens and he has this chlorine attached to him. So he has a new name. His name, well, I shall use a different color there. His name is chloromethane. Chloro suggests he has 1 chlorine in him. So I want you to write his name above because for the exam, you're going to have to memorize his name. Chloromethane. It's methane with chlorine in him. Exactly 1 chlorine. So here's what's going to happen now. This chloromethane, we're going to take him and we're not done with him. We are going to add more chlorine to him. So we're going to take the chloromethane now. Let me pretend we have a scoop and we scoop out all the chloromethane. We don't care about the HCl. We don't care about him. We are going to take him and add more chlorine. If we do this, more hydrogen is going to get what? Replaced. Look at what we have here now. We have 1 carbon, 3 hydrogens, and 1 chlorine. Now we are mixing it with 2 chlorines. 1, 2. Remember, alkenes will tend to undergo substitution reactions. The H's are the ones that get replaced. So you can choose any one of these H's, it doesn't matter. Let's just choose him. He is going to get booted out, and this chlorine is going to take its place. Now, if we do that, we will have what now? 1 carbon, 2 hydrogens now, because 1 hydrogen got substituted out, 1 more hydrogen. So it has 2 hydrogens. And how much chlorines will end up here now? How much Cl's should I write over here? 2. That's the Cl is taking this place. And of course, you had the Cl from before. And the H that gets booted out will join this chlorine who never moved in the first place. Isn't this and this the same? Look at it. It has 1 carbon, 2 hydrogens. Look up at the 2 here, symbolizing 2 hydrogens. And now it have how much chlorines? 2 chlorines. Right? And of course, it seems that in these reactions, you're always getting something real weird, but you're always getting HCl. The HCl is like the byproduct, right? He's the person that you end up getting, but you really don't care about it. Now, this methane has 2 chlorines in it. So you know what his name will be? But I think you all guess it. His name will be dichloromethane. Di means 2, right? It's a common term. Whenever you hear di in any sentence, it usually means 2 of something. So you all realize that the amount of hydrogens is getting less and the amount of chlorines is gradually getting more. Do you all see that concept? The H's are being replaced by chlorines. So naturally, the hydrogen values are getting smaller and the chlorine values are getting larger. Take down the red part, and of course, if you want the detailed explanation to go with it, take down the white part. Right, so we're going to take the dichloromethane and we're going to scoop it out and put it here, CH2Cl, right? Let's just forget if it's gas or whatnot, right? Let's just, to not confuse anything. We are going to mix it with more chlorine. Do you think you can predict what 2 things we will get here now? Right? Write it down, write down your answer. And of course, if you're brave enough, put your answer on the chat. Just take a try. Just take a try. You don't have to be correct. Somebody, I forgot the little 2 here, and you are correct. Okay. Right. So remember, what's going to happen? One of the chlorines that have 2 here right now, it's going to boot out one of the hydrogens, and a chlorine is going to take its place. So you're going to end up with C1 hydrogen now, and you're going to end up with 3 chlorines. And of course, they end up with HCl, the gas version of it. And his name, because it has 3 chlorines, it's trichloromethane. So you all notice in each case here, the hydrogen 1 at a time is getting booted out. It's not like all 3 are being replaced or 2 at a time is being replaced. It's 1 at a time. Hence the name substitution, one at a time. Do the last step for me. Take this chloromethane and do the final step for me. Take it and add chlorine one more time, and that will be the end, but mostly the end of this particular topic. So it only have one more H to replace, right? Only one more. So what's going to happen, right? He gets eventually removed, replaced by one of the chlorines. So now you have 4 chlorines, and unfortunately, you get back the HCl. And since it has 4 chlorines, you call it tetrachloromethane. And that's the end of it. Before you ask the question, since it have no more H's to replace, if we, at the same, if we were to mix it with more chlorine, would the carbon get replaced? And the answer is no, right? The carbon is just too difficult to remove. The hydrogens, which live on the outside of the structure, are the ones that get substituted out. All right? Great. So this is the end. CXC will only ask you up to 4 reactions. You will not have to even consider beyond that. So take down the answer and we will move. Moving downwards now, right? The next thing is alkenes can be cracked. Now, this one is pretty easy to understand. What we have over here, right, is a long chain hydrocarbon. Well, here's an alkene. This is definitely an alkene. I even gave you the name. It has 1, 2, 3, 4, 5, 6, 7. Okay? It has 7 carbons. So his name, if you look back on your chart, is hep. Don't ever mix up hep with hex. I used to mix it up, right? Hep is 7. Hex is 6. What you can do, and you see this alkane here, you can apply 2 things there. A lot of heat and a lot of pressure. And what happens, you can physically break this into 2 separate pieces. However, when you break it into 2 separate pieces, right? You see how you start off with an alkane? Now, let me zoom in a little bit here so some of you all can see it a little better. When you break this into 2, right? Remember, you started off with 1, 2, 3, 4, 5, 6, 7. When you break it, you end up with 2 pieces. But if you count up the amount of carbons, you still have 7. 1, 2, 3, 4, 5, and 6, and 7. Right? Obviously, if you break something up, you cannot end up with more. You have to end up with the same amount of pieces you started off with, obviously. But you all notice something funny here? When you broke it up into 2 pieces, you got an alkene, which we are very familiar with. And the name of this alkene is pentane. 1, 2, 3, 4, 5. But the other piece that you ended up, is this an alkene? Look at that carefully. Is that an alkene? The answer is no. And why is that not an alkene? Because alkenes only have single bonds. This one introduces something kind of new today. It has a double bond. Anything with a double bond is called an alkene. And it's so easy to mix up because both of them have the word al. And one is A-N-E and the other one is E-N-E. And it just so happens the name of this alkene, because it has 2 C's, you don't call it ethane, you call it ethene. Real easy to mix up unless you get enough practice. And that is what this summer is about. Lots of practice. Now, before you ask this question, whenever you apply heat and pressure, will it always break up into 1, 2, 3, 4, 5, and 1, 2? Not always, right? It's almost like a kind of random procedure a lot of the times, right? Sometimes it would break up such that instead of getting 5 here, you will get 1, 2, 3, 4. And if you get 4 here, you will get how much here? 1, 2, and 3, right? But usually if you apply the exact heat and pressure in the industry, most of the times you'll get the same result. But the thing about it is not always a perfect procedure, right? Because in the industry, you're trying to apply a certain amount of heat and pressure, but it's kind of hard to keep the pressure and heat exactly the same every single time you do it, right? So take down everything you need on the screen here. I won't give you 20 seconds, I'll give you a minute, because I know you have to draw and whatnot, right? And he is eating. Right. Let's move on now. So I'm thinking this is a real good time to introduce you all to alkenes, because this is probably the first time a lot of you all are seeing the item with a double bond. And I think we overstayed our welcome with alkenes. So let's change the topic a little bit. Alkenes, okay? So make this a little bit smaller. Now, alkenes obviously are different from alkenes. The general formula for alkenes, as you'll remember from last week, was CnH2n plus 2. It had a plus 2 at the end. Alkenes have a slightly different formula. The plus 2 is missing, right? And of course, the general formula always allows us to calculate the amount of hydrogens, provided that we know the amount of carbons. So here are some examples of alkenes, right? Now you notice the rules will be the same with regards to the amount of bonds leaving each carbon, the amount of bridges. Now look over here. You know it's an alkene because you're seeing one double bond. For CXC purposes, there will only be one double bond. It won't have 2 double bonds or 3 double bonds. And that's just not going to come for CXC exam. Look at this carbon here. It has 1, 2, 3, 4. Even this carbon here, it has 4. 1, 2, 3, and 4. Even this one, 1, 2, 3, and 4. So the rules still stay the same. Let's see if the formula actually works. For this alkene, it has how much carbons? 1, 2, 3, and 4. I want you all to use the formula to calculate the amount of hydrogens. We pretending the letter N is 4. If it has 4 carbons, the letter N is replaced by the number 4. How much hydrogens will it have? Obviously 8, right? 2 multiplied by 4 is 8. Let's count up the hydrogens and see if we really have 8. 1, 2, 3, 4, 5, 6, 7, and 8. So it is correct, right? The formula is correct. Do you all think you all can help me name these 2 alkenes? The concept is still the same, except the word would end in "ene." You know how alkenes is end with "ene"? What would be the name of the first one? Count the amount of carbons and replace it with the prefix. And you're getting this off the bat, right? So that is great. So it's 1, 2, 3, 4. That's bute. How about this guy here? The second one. 1, 2, 3, 4, 5. He is pent. Now there's a slight adjustment I need to make to the names here, all right? We just can't simply call this butene, all right? We have to tell the examiner where the bond is. Now, to reach the double bond, when I say the bond, I meant the double bond. You have to choose the shortest path to meet the double bond. So if you start on this side by mistake, the double bond is not connected here. He's 1, 2, and it seems that he's connected to the third one, but you have to take the shortest path. If you start from on this side, when you reach the very first carbon, you can stretch your hands out and touch the double bond. So on which carbon is the first double bond accessible? The first carbon. So there are two ways you could write the name, right? For this, I'm gonna go up a little bit so you all could, I'll make this a little smaller so you can see the whole slide. His name will be but-1-ene. Sometimes in certain textbooks, they will write it like this: 1-butene. But I believe this is the new way of writing it now. I believe the one on top is the old standard. This is the new standard now. So the one in between the dashes will tell the examiner where the double bond is. It's connected to the very, very first carbon. The next one here will be pent-1-ene. Because if you start to walk from on this side, as soon as you reach the first carbon, you have access to the double bond, right? So it's a pretty, to be honest, I would prefer if you use the underneath one. I'm not too clear on whether CXC accepts both answers. But usually in the newer textbooks and whatnot, I realize that they are using the one underneath. So I'm going to go with the one underneath. All right. Just as a safeguard. But your teacher might use the one on top. Let it slide for the time being until we reach closer to exam. And I could probably clarify which one CXC wants. All right. All right, so let's move on here. Oh, this one, we just did this one, right? On how to name alkenes. So I'm not going to, we already named this, so I'm not going to waste your time on this slide, right? All right. So let's talk about some isomers now of alkenes. Now, the isomers of alkenes for the CXC syllabus, I'm talking about just for the CXC syllabus, right? Is one of the easiest things you will ever do, right? Remember, an isomer are compounds that have, well, for organic chemistry in any case, that has the same amount of carbons and the same amount of hydrogens, except with what? Arranged in slightly different orders. What's the name of this alkene again? Look at it. It has a double bond, so I know it's an alkene. Who can tell me what's the name of this alkene again without looking back? It has 1, 2, 3, 4, 5, 6, right? And if we walk from this direction, the double bond is, we can first access it from standing up at the first carbon. So his name will be, well, the way I would prefer it, it's hex-1-ene. All right, if you put a number in front, I'm not going to judge you too hard, right? Right. So what would be an isomer of this? To make this an isomer, here's what you have to do, right? I'm just going to put back the 6 here, right? 1, 2, 3, 4, 5. Here's what I'm going to do. I'm just going to move the double bond. Instead of the double bond being here, I'm just going to move it up. I can move it here if I wish to. All I'm doing, if the examiner asks me to draw another isomer, I just have to move the position of the double bond. Now, you gotta be careful. If you move the double bond the arrangements of the hydrogen is going to change. A lot of students get it wrong at this point. Tell me if remember how it started off with 2 hydrogens here. Is it still okay to put 2 hydrogens here? Well, what do you all think? That's wrong, right? Because if I move the double bond and I concentrate on this carbon, how much bridges are leaving it? 1, 2, 1, 3. You need 4. So I have to add in an extra H here. And of course, when you reach this guy, he has 1, 2, 3. He has 1 hydrogen here to make it 4. Same thing with him here. He has 1, 2, 3. I could just put an extra hydrogen. The hydrogen could go on top, or the hydrogen could go underneath. Now, even with those changes, if you count up the amount of hydrogens and the amount of carbons, you're going to get what? The same. If you don't take my word for it, count up all the hydrogens here, count up all the hydrogens here. You're going to get the same exact amount. Meaning that if the amount of carbons and the amount of hydrogens is the same, but you notice the H's and things rearranged slightly different, and of course the double bond moved to a different position, it would be an isomer. What would be the name of this new isomer? Take a shot of it. Well, what would be the name of this isomer? Perfect. You guys are getting it correct. It's hex 2-ene, because the double bond is if we walk from this direction, the double bond is first accessible at the second carbon. And of course, I'm not going to do back a full diagram, but if I were to move the double bond over here, just putting it in orange, like I move this double bond and I put it here. If I were to do that, it would be how much? 1, 2, 3. It would be hex 3-ene. And if I move it over here now, the blue one, I'll put the blue, what would be its name? By the blue one. So I move the double bond up 1. Don't fall for the trick. It's a trick question. If you say hex 4-ene, because you say you start to walk from on this way, 1, 2, 3, 4, that would be wrong, because you have to choose the shortest path to reach it. So if I choose this side, it will be what? 1, 2. The double bond will be first accessible after the second carbon. So his name would actually be what? Hex 2-ene. You gotta be real careful with those little tricks in the exam. You always have to choose the shortest path to reaching the double bond, right? Some people are saying hex 3, it's not 3. Because if you start to walk from on this side, when you walk by this carbon, the first one, you cannot touch the double bond. But the minute you reach the second carbon and you're standing up here, you can just stretch your hand very, very easily and touch the double bond. So it happens at, right? Let's see what's next here. Now, right? So just like alkenes, right? Just like alkenes can undergo some reactions. At first glance, right? Remember, go back in the notes for the alkenes. How much types of reactions can alkenes undergo? How much categories did it have? It was 3, right? And I can prove that here. Let's go up. Actually, a few people said 4, some people said 5. Let's go back up here. Remember the 3 categories. You can burn it in air. It could go through substitution reactions. And of course, alkenes can be cracked. So it's 3 types of reactions, okay? Alkenes, right? At first glance, you must be saying, well, alkenes easier. Alkenes undergo how much types of reactions? it can burn in air or oxygen. So that's one. But instead of undergoing substitution reactions, it goes underneath a different type of reaction called an addition reaction. So it only has two categories. There's a little problem. Even though it's only two categories, the addition reaction, it have about 6 or 7 different types of addition reaction, making it a little bit harder than alkenes, only a little bit harder, okay? We're not going to be able to do the second one today, because this is going to take us a good 45 minutes to do, and we only have roughly 15 minutes. So let's at least do part 1, and there's a slight difference when it burns in oxygen. In our gas tanks, right? Remember I told you we use alkenes. We do not use alkenes, and there's a very good reason for it. Alkenes burn with a yellow flame. Nothing is wrong with the color yellow. That's not a problem at all. But when you burn it, it's not a clean flame. And here's an example. You just get a kind of smoke coming up, right? Now that smoke is actually carbon, unburnt carbon. Tell me something. Would you like to see this in your kitchen every time you light it a fire? That's not a good idea, right? Your ceiling is going to get black. You're going to be coughing and choking all the time, every time you cook your favorite food, whether it be bodi, whether it be chicken nuggets, or whatever you like, okay? Now you notice the reaction is almost the same, right? Right? I made a slight mistake, right? I'm supposed, I copy and pasted the other reaction by mistake, right? So here's what, just take down this for the time being. A yellow and smoky flame is produced. This here is the wrong reaction. But we're going to investigate why this is the wrong reaction. Remember, we're dealing with alkenes. So we're supposed to be burning an alkene. Is this an alkene? This is not an alkene. Remember, his name is what? Methane, okay? I would like you all to try to draw something called methane and tell me if that is possible. Methane has 1 carbon, but for it to be an alkene, it must have a double bond. The double bond has to be in between the carbons. Now, let me give you an example. Remember, for it to be an alkene, it must have double bonds in between the C's. Look at this one too. In between these 2 C's, it have a double bond. You are going to realize this is impossible to draw, because for it to be methane means that it only has 1 carbon. Is there another carbon for there to be a double bond in between? The answer is just simply no, which means methane is a made-up substance that doesn't exist in real life. The simplest alkene you can get is something called ethene, because ethene, S, means it has 2 carbons. I was supposed to put ethene here, not methane. So that's a mistake I will have to clear up next week. I will have to update this slide. It's laziness on my part. I just copy and pasted the formula from on top, and I forgot to edit it. All right. So for the time being, just take down everything I'm underlining here. Alkenes burn in air or oxygen. Take down a yellow smoky flame is produced. And you see this part here, take it down as well. It's why it burns with a smoky flame. It won't make too much sense as yet, but next week I'm going to take my time and explain it. When you are finished, let me know, but do not leave. We have to talk about the homework. When you go to the school website for homework, you are going to find today's recording. You obviously go to summer recorded classes. You'll see it on the menu itself. It's a very boring website. Everything is super easy to find. Just scroll down when you reach the summer recorded classes. Look for chemistry. Wednesday chemistry. Look, last week work is already up. That video is already up. I will insert it on top of this one by tomorrow so you can review the class. It's that simple, right? Summer recorded classes. Now, additionally, I want you to go into the chemistry classroom, and some of you all did not complete the beginner's homework as yet, which is the first 5 videos. And I also, addition to that now, I want you to do videos 1 and 2, which is balancing equations, right? And for those of, well, the rest of the videos right now are not available, but I will update it. So for those who want to do moles, like if you're just bored and you just want to do moles, you can review moles if you want to. But please concentrate on the beginners videos and the balancing equations. Everyone clear on what the homework is, right? Once you are clear on what the homework is, you are free to leave.